Okay, so I want to look at a few questions. We'll be taking the basic questions for this video, and then we'll take a few more complex ones later on. And before we start, the questions that we'll be taking for this session are coming from Fundamentals of Chemical Engineering Thermodynamics by Kevin D. Dam and Donald P. Visco. But as time progresses, we'll be picking questions from other materials as well. So this is just to help us with the fundamentals. And remember these two equations we derived earlier. We'll be using them today. Okay, so we have this example. The liquid molar enthalpy for a binary mixture of benzene and cyclohexane can be described at 25 degrees Celsius and 1 bar by this expression. So benzene is species 1, cyclohexane is species 2. So everywhere we see x1 is going to be for benzene, and everywhere we see x2 is going to be for cyclohexane. Everything with the subscript 1 is for benzene, everything with the subscript 2 is for cyclohexane. And we are being told here in the first part of the question that what are the partial molar enthalpies of benzene and cyclohexane in the mixture when they are equimolar at 25 degrees Celsius and 1 bar. So we are looking for H1 and H2 for benzene and then for cyclohexane. And remember we said the partial molar property depends on the number of moles of the species present, right? So if we are told that it's an equimolar mixture, then it means that N1 is equal to N2, right? And this would also indicate that our X1 is equal to our X2 and should be equal to 0.5 because it's equimolar, so the mole fractions would be the same and the number of moles would be the same. When the mole fractions are supposed to be the same, because the total sum is supposed to be 1, then the sum of one would just be the sum of one of them the value of one of them would be 0.5. Or to make this a little bit more understandable, we know that n1 plus n2 should give us n total, right? But we are saying that n1 is equal to n2, so n1 plus n1 should give us n total because n1 is equal to n2. If I have 2n1 to be equal to my nt, if I divide 2 by nt, I would get 2x1 is equal to 1. So x1 is equal to 1 over 2, that's 0.5. That will be the same as x2 because it's equimolar, right? So that's just by the way. So we'll first find the partial molar enthalpies for both of them in the equimolar sense. And then we'll find the B says that we should find the pure components molar enthalpy of cyclohexane at 25 degrees Celsius and at 1 bar. So if it's now going to be the pure components molar enthalpy, then x2, that's the mole fraction for cyclohexane, will be 1, and then x1 for benzene will be 0. Because we're looking at it being purely cyclohexane, there should be no benzene. That's why the mole fraction of benzene is going to 0, and it should be only cyclohexane. That's why the mole fraction of cyclohexane is 1. So we have the expression. We had h bar to be equal to minus 3399. I'm coming. Okay. Plus 4516x1 minus 3215 x1 squared. And we said that if I want to find a partial molar for species 1, it's going to be h bar then plus x2 dh dx1, and I'm taking this from equation 1, so I'm looking for h1. So in this case my m is going to be h. Remember, m stands for any property at all, be it enthalpy, volume, internal energy, anything at all. So now you're looking at enthalpy, so h1 is going to be h bar plus x2 dh dx1. So that's what we are going to use. So I'll first have to find this part here. So I'm going to differentiate this equation to get that. So I would have, if I'm differentiating with respect to x1, I'll get h bar to be equal to minus 3399. No, sorry, this will go to 0. It's a constant. If I differentiate this, so the constant goes to 0. So I'll have 4516 minus 2 times 3215 x1. So this is going to give me 4516 minus that's going to be 6430. Yes, 6430 x1. So Okay, so that's it. Now what's going to happen is that I'm now going to fit this into this expression now. So h1 partial molar is going to be equal to h bar, which is this expression up here. So that's minus 3399 plus 4516 x1 minus 3215 x1 squared plus x2 times the dh dx1. So plus x2 multiplying, so this is the dh bar dx1, so we're going to multiply this expression. So 4516 minus 6430 x1. Now we said it's going to be equimolar. So if that's the case, it means that x1 is equal to 0.5 and x2 is also 0.5. So I can put those values in this, and when I do that, what I should be getting would be so minus 3399 4516 and a second. Okay, so what I'll be getting is minus 1294.25. This is what I'll get. And then the units, okay, the units were not given, so it's going to be this, probably in joule per mole or so, or kilojoule per mole. Yes, but then this is the numerical value that we are supposed to get, right? So we can do this for the pure component, the partial molar for species 2 as well. So I'll do that on the next page. So I will have here my h2 to be equal to my h bar minus x1 dh dx1. I've already found the h dx1 and I already know my h bar, so I'll just put that in there. So that would be the minus 3399 plus 4516 minus 3215 x squared. So that's for the h bar part. Then minus x1, and then the dh dx1 we had 4516 minus 6430 x1. So 4516 minus 6430 x1. So this is what we are going to have. And if I should put that, if I should calculate this, so this is x1. If I should put in my value of x1 to be 0.5, I'll be getting my value to be minus 2595.25. So this is what it's going to be for H2. Then the next part of the question said that what is the pure component molar enthalpy of cyclohexane at 25 degrees Celsius. So for the pure component molar enthalpy, right, we are going to use x2 to be equal to 1 and x1 to be equal to 0. So let's look at something. I'm looking for, when it is pure, the partial molar for H2 would be the same as the pure molar point. So x1 is going to be 0, right? So it means that from this expression up here, I will be getting just h bar minus 0 times dh dx1. And at the end of the day, it's just going to give me h bar, right? Now, so what we are saying is that if you're looking at the partial molar for cyclohexane, but it's only cyclohexane that's present, it's purely cyclohexane, then that value is going to be the same as the pure molar property. That's what we are saying by this. And if we should still work with this expression we have up here, right, and we are saying it's pure, x1 is going to be 0 because x1 is for the benzene. So if x1 is 0, then this whole term goes away to 0, so that we are left with just this. So for my h2 bar, I can just use the expression for the h, which was the minus 3399 plus 4516 minus 3215 x1 squared. But once again, x1 is going to be 0, so this whole term can go to 0. There's supposed to be an x1 here. There's supposed to be an x1 here. Sorry about that. Yes, it's supposed to be an x1 here. So this value is still correct though. So this one will also go to 0. So my final answer will be minus 3399. Right, so that's what we have to keep in mind. So usually when you're asked to find a pure component molar enthalpy of any species, you don't need to go to the differentiation part, because it's very likely that that side might tend to 0. So if it is the pure molar enthalpy of cyclohexane is x2. So if x2 was in this expression, you make it 1, and then you make x1 0. If it was the other way, where you're looking for the pure component molar enthalpy of the benzene, you rather make x2 0 and you make x1 1. So if that was the case, if we're looking for the pure component molar enthalpy of benzene instead, realize that x2 is 0. So we'll come back to this expression here. So here we'll have our h1 bar to be equal to our h bar. Then we said x2 be 0. So that's still going to be the same h bar. Right. So the long and short of this is that if you're looking for the pure component molar enthalpy of something, you don't need to go through the differentiation. You can just pick this expression here. If it is the pure component molar enthalpy for species 1, then x1 is 1. If it is for species 2, then x2 is 1. And then the other one would be 0. So that's what we are trying to see. Okay, so that's it for the first question. For the second question, it's a very similar approach. The liquid molar volume for a binary mixture of methanol and water can be described at 25 degrees Celsius and 1 bar by this expression. So methanol is species 1 and water is species 2. Now, we've been given the expression and we are supposed to estimate the molar volume of the mixture of 75% methanol. So it means that x1 is going to be 0.75 and x2 is going to be 0.25. So let's try this out. We have the expression to be v is equal to, sorry, I have to go back and forth to see the expressions properly. So this 18.102 plus 18.491 x1 plus 4.1506 x1 squared. So we know that if it's v1, it's going to be v plus x2 dv dx1, and if it's v2, it's going to be v minus x1 dv dx1. So we'll find dv dx1 first. So that's going to be 18.491 plus 2 times 4.1506 x1. Now I can put this into these two expressions here. So I'll do it for the first one. v1 is going to be v bar, that's this expression up here. So that's 18.102 plus 18.491 x1 plus 4.1506 x1 squared, then plus x2 times the dv dx1. So x2 times 18.491 plus 2 4.1506 x1. Let me use this instead. So we said x1 was 0.75 and x2 was 0.25, so we can put that into these two expressions. So let me quickly get it in my calculator. Okay. $18.491 plus 2 times 4.1506 x1. Okay, so we said x1 is 0.75 and x is 0.25. So from what I'm getting my v1 to be 40.4842. So you can verify this, right? Then v2 is going to be this expression here. So I'll still have my v bar, so that's my 18.102 plus my 18.491 x1 plus my 4.1506 x1 squared, then plus, no, sorry, minus, so minus x1 now, so minus x1 times the dvd x1, which is the 18.491 plus 2 brackets 4.1506 x1. Sorry for how the handwriting is. I think let me do this part properly. 2 and then 4.1506 x1. So if we should also put this in, what we would get is going to be what I'm guessing is 15.7673. So once again, let's verify the calculations ourselves as well. Now find the partial molar property values for methanol and water as these conditions with the composition given in A. Okay, so I think what we rather did right now was for B. We found the partial molar properties, right? And the question was like we should estimate the molar volume of the mixture of 75% methanol. So for the A, this is not the partial molar, it's the molar volume, which is this what we have here. So to estimate this, I just need to put in 0.75 wherever I see x1, because x1 is the composition for methanol, right? So what we've done is for the B, finding the partial molar value, property values for methanol and water at these conditions. So the partial molar values that we needed to use our expression, where we needed to use these expressions. And then if it's just the molar volume or just the molar property, that's this expression here. So we already have the expression for it. So I just put in 0.75 into this expression, and that should give me I'm coming. So that should give me, that's 34.30496. So once again, let's verify all the final answers. Okay, this is the last question we'll be taking for today. That the density of an equal mass water and ethanol mixture is 0.913 gram per cubic centimeter. So water is 1, ethanol is 2. If the density of water is this and that of ethanol is this, so that's for the density when they are pure, right? With both at 20 degrees Celsius, does this equal mass mixture possess any positive or negative excess volume at 20 degrees Celsius? So we have water to be 1, ethanol to be 2. We have the density of the mixture to be 0.913. Then we've been told that the density of just the water is 0.998, and that of the ethanol alone is 0.789, and we've been given an equal mass mixture. So there are two ways to go about this. I think I should speak about both of them. We can actually start by using a basis, right? So we can say that maybe let's say the mass of water, sorry about that. So we can say that we can let the mass of water be equal to 1 kilogram, because it's an equal mass mixture. So the mass of the ethanol as well, right? Well, let me use the numbers. So water is 1 and ethanol, sorry, is 2. It's also going to be 1 kilogram. So the total mass is going to be 2 kilograms. Then we know that density is equal to our mass over our volume. So if I want to find the volume, I can use the mass over the density. So for the mixture, right, the volume of the mixture is going to be the total mass, that's the 2, over the total density, that is 0.913. So that's going to give me so it's going to give me 2.19058, and the unit is going to be in cubic centimeter, right? That's for the mixture. Then for each of them, so for water, the volume is going to be the mass, that's the 1, over its density, that's 0.998. So that's going to give me 1.002 cm cube. And then for the ethanol, I think let me do the ethanol. Let me put that one here. So for the ethanol, the volume is going to be its mass, which is also 1 over its density, which is the 0.789. So that's also going to give me 1.2674 cm cube. Now I can find the, so we are doing this because we said it's an equal mass mixture, so the mass of water and ethanol will be the same. So the mass, if I use 1 kilogram of water, I should use 1 kilogram of ethanol. So that's what is informing the mass that we are using here. And then the total mass is 2, so that's what's giving us this, right? So now we have what we are expecting from the mixture in the real case, because when we mix them, this was what the density was, right? But then when we have them individually, this was the this is the volume we would get from the ethanol, this is the volume we get from the water. If we should add them, so let me also do that here. If we should add them, so if I should add v1 and v2, what I'm getting is so that's 1.2674 plus the 1.002, right? So 1.2674 plus the 1.002 all in cm cube. What I'm getting is 2.2694 cm cube. So if we are looking at it in the ideal sense, the volume of ethanol was 1.2674 and that of water was 1.002. So if we should mix them, ideally we should get this. But the actual volume we are getting is 2.19058, right? So if we want to find the excess volume, so let me just use V excess here. It's going to be the real volume. So that's this one here. So that's the 2.19058 minus the ideal volume, the 2.2694. So sorry, okay. So so yes, we're getting 2.2694 minus 2.19058. So that should give us something about, wait a second. So it's supposed to be real minus ideal, not ideal minus real, sorry. So it's supposed to be this rather minus the 2.26 4. So we should be getting a value of about negative 0.073 or so cm cube as the excess property. So it's going to be a negative excess volume, right? Sorry that everything had to be cleared. We're having a little issue with the writing pad, so but that's the whole concept. So you can assume a basis, find the volume in the real case, which is going to be based on the density of the mixture, what was actually measured, the density that was actually measured after the mixing was done. That would be the real case. So you can find the volume in that sense, the real volume. Then we can now find the individual volumes when they are pure and then mix them together. When we do that, what we'll be getting is the ideal volume, what we're actually expecting. So the volume of the first plus the volume of the second, right? And then if we should find the difference between this, it will give us the excess volume. Okay, now remember we spoke quite a lot about the whole issue of if it is an ideal case, we can blend the property. Someone might think that because it's an equal mass mixture, I might have to do 0.5 of V1 plus 0.5 of V2. Not in this case. So we would actually apply something like this for the other way of solving the question. It won't work in this case because you realize that the moment we find the volume in cm cube, it's not specific, right? So we don't need to multiply by the mole fraction. Is that okay? Or we don't need to, in this case, we don't need to multiply by the mass fraction, right? So if it was supposed to be specific, we'd have cm cube per kilogram. That's the same as 1 over the density. So remember we had something like this where if we had it in the specific form, it was going to be x1 h1 plus x2 h2 all the way to the end. If it was not in the specific form, it was just going to be n times h1 plus, so n1 n2 times h2. That's if it's in moles. If it's in mass, it would be the masses. So this might be m, right? Now what we had in the first case was even if we take it that it was specific, we had cm cube per kilogram, right? Now what we did was that we multiplied through by their masses so that we can get it in cm cube, so that is no longer specific. And that happened, so we said cm cube over kg is going to be the one over the density. If we multiply by the mass, that ends up giving us just the volume. So in this case, you don't need to now multiply by the mole fraction again. It will be more like repeating something in a way, right? So we don't need to do that in this case. We can just find the volume and then just add them, right? So in the case that you have maybe even if let's say we have enthalpy, so maybe you have 2 joule per mole and then 3 joule per mole. If you should end up multiplying them by their number of moles, right, you end up getting, so let's say it's equimolar and it's 1 mole, 1 mole, right? We'll have 2 joules and then 3 joules. We can add them to get 5 joules. We don't need to multiply that again by the mole fraction. So just keep that in mind. Okay. Now, the other method we could use is that we have the density given to us in gram per cm cube. And as I was saying, we could have made it specific. So we could have found the inverse so that we have it in cm cube per gram, right? So let's do that for the mixture. So for the mixture, we had the density and then we have 1 over the density. So let's do this. So for the mixture, density was 0.913 for water, that was 1, and then ethanol is 2. So for water it was 0.998, so this is in gram per cm cube, and then for ethanol it was 0.789. Right, so all in gram per cm cube. So this is going to be in cm cube per gram. So let's find their inverses. So the first one is going to be 1.09529. The second is going to be 1.002, and then the last is going to be 1.2674. Now we can take it from here. We have the specific volume now, right, in the real case to be the 1.09529 cm cube per gram. If I'm going to keep it in the specific form, that's when I'll now need to work with my mole fractions. So the mole fraction is going to be 0.5 for so no mole fraction, mass fraction 0.5 for both of them, because it's supposed to be an equal mass mixture, right? So my for the real case, for my v real, is going to be my x1 then my v1 bar plus my x2 then my v2 bar. So it's specific. Yes, okay, I think that's fine. So x1 0.5 times the 1.09529 plus 0.5 times the 1.2674. I actually prefer this method to the method of finding a basis, so you can consider that 2674. So if we do this, what we will be getting here is 1.181345 cm cube per gram. So we can now find our Vxs to be our V real minus our V ideal. So I'll do that at the top here. So for the real one, we are going to have this here. So that's the 1.09529. And then the ideal one is going to be this down here, 1.181345 So if I should find the difference, it will give me I think that's minus 0.086055 cm cube per gram. Yes, I think that's it. Yeah, I think that's it. Okay, so that's what we'll be getting. So once again, verify the calculations and the values, and then let's see what we get. Okay, so I think that would be it for today. Okay, so thank you for your time.